Okay. Right, so obviously we've finished the second test. Who was in Math Lecture Room 1? Was anyone here in MLR 1? Was there a problem? Was there an issue in MLR 1 with the people running it?
Oh, she just wouldn't let us rip off that formula sheet.
Pardon?
She just wouldn't let us rip off the formula sheet.
She wouldn't let you remove the... Who? Kathleen, the older lady? Right. Was there another problem though? Yeah, that's bad. But was there another problem? Like noise or something? Was there lots of noise in MLR1 from construction? No? Oh, okay. I heard there was a problem, so... Anyway, good. Sorry about not removing the formula sheet though. Now, yeah, obviously it's all been done. As before, I've given it to my markers, so obviously this is a big class. So I've given my markers till next Friday to mark it. Now obviously that's after all the lectures, so you won't be able to, you won't get your test papers back before the semester's finished. So what will happen is hopefully next Friday I'll get them all back, and same deal as the first one. I'll send out a message saying they're done, which means I actually physically have the papers in my possession. I'll upload solutions, but you'll have to come to my office during my consultation time, during the study break, and up until your final exam. I'm going to have a lot more consultation time than normal, because obviously I've finished teaching as well. So there'll be plenty of opportunity for you to come and grab it, but they certainly won't be ready by the last practical class next week. This class is too big, okay? So other than that though, what do we think? Okay? Yeah, not too bad? Not hearing a resounding, that was good, all right, but hopefully, I'm sure it'll be fine, so, yeah, anyway. I've also uploaded your next so-and-so assessment, which is due this Sunday, so standard 5 questions as normal. We're almost finished with that too. Okay. Now, last thing we did last week was we're looking at a concept of a path integral, right? And what we were doing basically is this, imagine we've got some curve, so this is in 3 dimensions obviously. Imagine we've got some curve, the blue curve in the XY plane. Imagine that it's like a curtain, right? And that you pull that up, and where that intersects some surface, that's going to define some line that sits in some surface. That's the projection, the red line, right? And then you can find the area of that curtain. So the area bound by a curtain that goes from the plane to some region in the XY plane as a path integral, sometimes also called a line integral. And we write it in shorthand notation like this. So this area here is the integral of f, where the function f is the surface evaluated directly above this blue curve. So that's with x and y replaced with its suitable parameterization in terms of t. So we read this in words as this is the integral of f along the curve C with respect to length along the curve. That's what the ds means. S is a symbol we use, something that we call arc length. Essentially, S is a measure that sort of measures your length along this curve. If you go on and do more vector calculus, you'll learn a lot more about what things you can do with arc length and things like that. Right? So, but there are, in 2 dimensions, there are 2 other integrals we might want. And so if you imagine if you're standing here looking at this thing, what's the area of the bit you see? Or in other words, you take that bit, you squash it into the XZ plane, what's that area? Or you squash it into the YZ plane, what's that area? So it's shadow, basically. And these 2 we can also do by path integrals. And so with respect to x means we've projected z into the xz plane. And this area is this one where y means we've projected z into the yz plane. So when I ask you to do a path integral, in 2 dimensions anyway, you've got to take note, am I saying ds, which means find this area, dx, find this area, or dy means finding this area. And quite often we mix these up, so it looks a little bit weird. I'll show you that when we get to an example. All right, but the first one we did this is basically the definition we did last week. Right? It's f evaluated t times the length of the tangent vector, which is the square root of the derivative of the x component squared plus the y component squared. So this is basically this written out where r is some parameterization. We're sticking with 3 dimensions, so this is just the length of a vector x dash y dash, basically, right? As in terms of t. Right, but along the x-axis, the formula is a little bit different. So this bit you multiply by is just x dash and y dash, right? And it kind of makes sense, although you can't think of it this way, right? Think of it kind of like Pythagoras. It's not correct to think of it this way, but essentially, imagine if this was a straight line, right? So this is just some solid plane. You can imagine the length of that is the square root of the length of that squared plus the length of that squared, right? So you can sort of see that that's how they're written, right? So in other words, you could also think of it as dx means set y dash equal to 0, right? Because then you just get the square root of x dash squared, which is just x dash. And the same with this one, right? All 3 of these are on the formula sheet, so you don't have to memorise these formulas. All you got to do is take into account if I ask ds, dx or dy, which one you have to use, which one I'm asking for. All right? All right, so as an example, and this is where we often mix it up, right? Because at the moment, that looks weird, right? And I personally hate this notation, but it's what people do, right? So I could ask you a path integral like this: y squared dx plus x dy. That notation looks odd, right? It's implied that's what that means, right? Because you shouldn't have a dx over here. It's supposed to be at the end, right? So this one's a bit weird. So whenever I get the ones where these differential bits are mixed up, that's taken to mean this is actually 2 separate integrals over the same path, right? So often we write it like this, which is terrible, but that's what we do. But that's actually what it means, right? So this is written back to normal. So in other words, what I'm asking for here is that I've got some function, I'm asking for the area of 2 things, right? So the first one would be if this is the surface y squared, I'm asking for that area of under y squared plus that area under x, basically, right? So you see how we often mix them up, right? So first thing, the path here is a straight line connecting 2 points. We saw last week the quickest, simplest, dirtiest way to get a parametric representation of a straight line is just make it work, right? End point, and that should be a comma, not a full stop. So that bit is meant to be a comma. I will fix that. That's freaking terrible, right? End point plus start point plus end point minus start point. And again, we see why this works. When t equals 0, you're at the beginning because the t equals 0 wipes out the bit in the square brackets. And when t equals 1, you're at the end because the 2 start bits cancel, right? So it works, and then you get a nice integral from t equals 0 to 1, right? So that's our parameterization. I need its derivative, right? So that's x dash y dash. So y squared dx is, you replace y with its parameterization in t times x dash, right? And that's what you're integrating from 0 to 1. Then this bit, you replace x with its parameterization in t times y dash, right? And then what I'm actually asking is you just add them up. Okay? But often we mix these things up. So the main thing is when I ask you one of these questions, you've got to take into account what I'm asking. And if we have a quick look at the formula sheet, I give you all of these. So they should be here somewhere. Where are they? Right, there's ds, dx, dy. Right? Now these ideas do extend to higher dimensions, but then we can't visualise what the hell is going on. So most of the time I'll just ask you 3D ones, okay? Now I have some examples here. So here I'm asking you to, essentially I'm asking you to calculate 3 different path integrals here. So this is the standard one from last week because it's ds, but this one is 2. It's y dx plus x dy, right? And another straight line connecting 2 points. So as always, I come up with a parameterisation first, and of course you can see why it works. When t equals 0, I'm at the point 1, 2. And when t equals 1, I'm at 9, 8, which is exactly what I need it to do. Right, so that's your x, that's your y. I need their derivatives as well. So ds means I want x times y, so this times the length of the tangent vector. And I just do this integral, not too bad. This one is technically 2 integrals. All right, you just attack each one separately and then add them together. And you can go to higher dimensions, and the process is exactly the same. You just can't visualise this, what's this going on. So this one's actually asking for 3 different path integrals. So the easiest way is to split it up. So this is y dx plus z dy plus x dz. Right? So we're integrating a 4D surface over a 3D line in space. So you can't visualise the area per se, because you can't visualise the 4D surface, but it's still an area. And here I've already given you the parametric representation of the curve I want you to do it over. So x is t, y is t squared, z is t cubed, and t goes from 0 to 1. So it's basically just a matter of plugging everything in with the formula on the formula sheet and doing it. So I need x dash, y dash, and z dash. This is actually supposed to represent 3 separate integrals, path integrals, and then you just do each one. So y dx, so y replaced with t times x dash, z dy, z replaced with t times y dash, x dz, x replaced with t times z dash. So you've got to take into account if I'm at dx, dy, in this case dz as well, or ds, where I want them all. Right? The question will make it obvious. You just got to look at the differential bit. Right? You just plug it all in, then you just add them all up. That's it. Okay? All right. So we've seen how we can use integrals to calculate all sorts of things. The last thing we can do with integrals, so in its basic form, integrating a function of a single variable, we find an area. Double integral was a volume. Triple integral is volumes as well, but depending on what we're doing, either 3D volumes or high dimensional volumes. And we've seen other things as well, like we can do volumes of revolution to find the volume of things. We can find lengths of curves, and now we see that the curves can either be explicit, y equals f of x, or implicit, right, where or parametric, right, and that lets us handle higher dimensional curves. And now this one with the idea of a curtain, right. The last thing we can do with integrals is surface areas, and this leads to something called a surface integral, which we're not going to do. We're going to stop at surface areas. Right, so the last thing we can do is calculate surface areas, and we've done several things like with the sphere. For example, when we did volumes of revolution, we proved from first principles that the volume of a sphere is 4/3 pi r cubed. Right? We proved it, thinking of a circle, revolving it around. There's a couple of ways you could do it. You could do it as a double integral as well, or you could do it as a triple integral in spherical coordinates. That's actually the easiest way to do it, and derive all these area formulas. Another one is, well, we know the surface area of a sphere is 4 pi r squared. We all know that. We'll use that at some stage. Prove it. Right? How would you prove that the area of a sphere is indeed 4 pi r squared? Right? And you can do that with integrals, because we can use integrals actually to calculate surface areas. And this isn't too much of a stretch. We've seen if we can calculate lengths of curves with a single integral, right, we can find the length of any curve as a single integral, either explicitly or parametrically. Right? Area is just length in the next dimension. We should be able to do that too. Right? And of course we can. But before we get to there, we have to work out how we represent a surface parametrically. So far, we've only done lines as parametric representations. right? And we bring in a variable t and we parameterize it. We can also do the same thing with surfaces. However, in this case, the parametric representations can be quite difficult. Either we will use coordinate systems we're familiar with, cylindrical or spherical coordinate systems, or we just brute force it, right, all the time. Coming up with a really clever one, much harder with surfaces, right? So if we've got a line or a curve or something in 2 dimensions or 3 dimensions, of course we only need one variable to parameterize it. And what that variable is basically doing is, imagine we're walking along this thing. The variable is like a coordinate, a single coordinate that follows us. When t equals 0, we're here. When t equals 1, we're here. Now, if I'm walking along a surface, right, no matter how complicated it is, I need 2 things to tell me where I am on it, don't I? Right? Imagine like an xy coordinate system that's following you along the surface. So to find a parametric representation of a surface, we need 2 variables. Right? And we usually use u and v. It doesn't really matter what the hell letter we use, but generally we use u and v. And you're already familiar with this. So when you get GPS coordinates on the surface of the Earth, we use spherical coordinates, and our parameters are longitude and latitude, the 2 angles in the spherical coordinate system. Because obviously the radius of the Earth is fixed, right? So remember, spherical's basically radius and these 2 angles. The radius is fixed on the surface of the Earth, so the 2 angles will determine your point anywhere on the surface of the Earth. You parameterize the surface of the Earth using spherical coordinates, right? And your 2 angles become your new variables, right? Right, so we need 2 variables, and a classic one is if I've come up with our using spherical coordinates on the Earth and say, for simplicity's sake, say its radius is 1, whatever unit that is. Don't ask me what the radius of the Earth is, I have no freaking idea, but whatever it is, say it's 1, right, in our suitably defined coordinate system. So remember, x is rho cos theta sine phi, y is rho sine theta sine phi, and z is rho cos phi, right, in our spherical coordinates rho theta phi. If I just call theta and phi u and v, because that's what we normally use for parametrics, rho is fixed, so I can take it out, basically. That's our coordinate system on the Earth, and that's actually how we do it, right? And in fact, this is actually how these, when we look at a map of the Earth, right, we use a 2D, we're trying to use a 2D representation of a 3D sphere, basically. And the way these work is we use this spherical coordinate system with the radius fixed. Right, so I've actually created this thing using spherical coordinates. Right? So if I take this one and like roughly map out all the boundaries of all the countries and continents, continents and things like that. If I want to represent this as a map like we normally do, now this is pretty rough, obviously, this wouldn't be a good map to use, right? But basically I'm taking x, y and z, for each x, y and z, I calculate, I can undo these, I calculate the corresponding u and v, and I can plot them on a 2D thing, right? So that's u and v, basically, right? Longitude and latitude, more or less. Right, so using what we've learned for paths, I can find, I can try and figure out how to calculate surface areas. Now think back to when we find the length of a curve in parametric representation, right, what do I need? When I look at this formula, I need the function evaluated at, with my coordinates replaced with their parameterization in terms of t, and I need to do something with the tangent vector. Right, so the idea is we have to do the same thing, but of course when we have a surface with 2 variables, we have 2 tangent vectors, right, because we're in 2 directions. So here I've got some representation of some surface in terms of my new coordinates u and v, and I need the partial derivatives with respect to my new coordinates. So these define these 2 tangent vectors. Right? Right, so since the surface depends on 2 parameters, we've got the 2 tangent vectors. And we remember, like when we were doing things like calculating tangent planes and things, instead of working with these two and having to work with two, we do the cross product and work with one, right? So obviously anywhere on the surface we've got these two tangent vectors and then one normal vector which always points outside, right? So I can use the dot product, the cross product, to calculate the normal vector, all right? So here's an example. Let's say we've got to find a parametric representation of the surface z equals x squared minus y cubed. Now, if we're doing parametric forms of lines, we can use the fundamental trig property sine squared plus cos squared equals 1 and try and make that work to make the parameterising easy. This is much more difficult for surfaces. You remember when we started looking at cylindrical and spherical coordinates, I showed you that pictures from that book that had lots and lots of coordinate systems in it? Right? So a lot of the time is if you've got a weird geometry, right, what I would do is look at that book and see if one works. Right? We're only going to do cylindrical and spherical or brute force it. Right? Now, so of course cylindrical are ones where we've got x squared plus y squared in there somewhere. Right? So if there's an x squared plus y squared, cylindrical might help. Right? If there's an x squared plus y squared plus z squared, spherical might help, because obviously cylindrical coordinates are cylinders, x squared plus y squared equals r squared. Spherical coordinates are spheres, x squared plus y squared plus z squared equals rho squared. Anything else, we brute force it. Right? And what I mean by brute force is the same with when we were doing lines. Let x equal t, y becomes f of t. Yeah? Here we unless it's cylindrical or spherical, or I tell you what the parameterisation is, you brute force it. Let x equal u, y equal v, z becomes u and v. Right? We just brute force it. Right, so this one we've got x squared minus y cubed, and I've got x going, I'm interested in the portion where x goes from 0 to 1, y goes from 0 to 4. Right, so because that's not x squared plus y squared or x squared plus y squared plus z squared, I just brute force it. Right, and a suitable parameterisation is you let x equal u, y equal v, and then z is just u squared minus v cubed. So basically you're just doing it in terms of x and y. Right, right, so that's a suitable parameterisation. Right, so you're really not doing anything. Right? What about this one? Last week we looked at, we found the volume of a, is that what we did? We found when did we do that? The cone, a couple, I can't remember now, hang on, sorry. When was that? When did we do that one? Was it week 9? No, must have been week 10. We did, sorry, where is it? Ah, here we go. The volume, we did this question where we found the volume of a cone. Now, we can use surface integrals to calculate the area of the surface of this cone. That's what we're going to do eventually. Right? But remember, we had this, basically the surface of the cone is the equation x squared plus y squared equals a squared times 1 minus z on h all squared. Right? Where h is its height and a is the radius of the biggest bit down the bottom. Right? So if we wanted to come up with a suitable parameterisation for this, the presence of the x squared plus y squared tells me cylindrical coordinates might help. Right? Right, because that's a picture, basically a picture of it. If I let x be r cos theta and y be r sin theta, right, then that's what my surface comes in cylindrical coordinates. So of course here I could come up with, that's r, and so the r, by the equation describing the thing, r is this. So a suitable parameterisation would be x is r cos v, y is r sin v. So the two variables here are z, its height, and the angle that sweeps out the cone, right? So a suitable parameterisation, my two variables are u and v. So they're just the height z and the angle theta. R is fixed because R is linked, not fixed, but R is linked, right? So that's a suitable parameterisation. Right? Now, they may not look it. If we were to calculate things, this parameterisation is actually much easier to use. Okay? Right, so I've got some examples here. No, that's last one. Hang on, where are they? Let's have a look at this one. Consider a surface with this parametric form. Right? What is this surface describing? Right? Well, when I look at it, I see x is 2 cos u, y is v, and z is 2 sine u. Now, of course, I could try and plot that in terms of u and v coordinates, but that's not telling me what the parameterization looks like. Right, so, but you'll notice the fact that we've got x is 2 cos u and y is 2 sine u, z is 2 sine u, I can see, well, that must mean that x squared plus y squared is a constant. Right? So this is parameterization is a cylinder, but it's not in cylindrical coordinates. The cylinder's pointing the wrong way. Right? Because cylindrical is x squared plus y squared, and slices of constant z are spheres. This is one where slices of constant y are circles. Right? So this is a parameterization of a cylinder that lies along the y-axis instead. Right? Now, find a parametric form for this thing. Now, again, what we do is either it's cylindrical, spherical, or we brute force it. Right? We don't try and be clever with the sine squared plus cos squared equals 1, because there are 2 variables now that may or may not work. Right? And for us, we'll say it's never going to work. Right? So this one, because it's x squared plus 2y squared, now you could try and let x equal, say, I don't know, cos of theta and y equal, what, 1 on root 2 sine of theta or something like that. Right? You could do it that way, but that will be a weird coordinate system that you'll have a lot of trouble visualising. Right? That's actually elliptical spheroidal coordinates. So that's where, you know, sphericals are where you get spheres, elliptical coordinates are where you get ellipses, like footballs, ellipsoids, football. But we're not going to do that, the hell with that. Right? So we're just going to brute force it. Basically, you just let x is u, y is v, then z is u squared plus 2v squared. That's it. Right? And that's what I mean by parameterizing the surface. Okay? For a sphere, spherical coordinates. Right? So this is the same as one with the coordinates of the Earth. So the radius here is fixed. So your r or rho, isn't it we used? Your rho is fixed, so your 2 angles, theta and phi, are your 2 new coordinates, right? The main thing is when we do surfaces, you want only 2. Just like when you do lines, you only want 1 variable t that describes the whole thing. For surfaces, you only want 2 variables that we usually call u and v. Of course, it makes no difference what you call them. That describes positions on the surface. So you're not describing the whole thing, its volume, you're just describing what it's like sitting on it. Right? Just like when you do a parametric representation of a line, you're describing as if you're walking along the line. You don't care about what else is going on. For surfaces, you're just walking along the surface, but you need 2 coordinates. Right? And once you've mastered that, and we're going to keep it relatively simple, we can actually do surface integrals. Now, I want to talk about that next week because I want you to practice doing the parametric representations. But just to show you what we're getting at, we know that the surface area of a sphere is 4 pi r squared. So we've proved a couple of weeks ago that the volume of a sphere, imagine we didn't know it was 4/3 pi r cubed. Right? We didn't know that. There's a couple of ways we've done it. We've done it by rotating a circle around about the x-axis, the volume of revolution. We've also done it as a double integral, and we've also done it as a triple integral in spherical coordinates, right? We've proved the same thing 3 different ways, right? So hopefully you are all convinced, yes, that is the correct answer for a sphere. What about the surface area? We know the surface area is 4 pi r squared, which is curiously the derivative of 4/3 pi r cubed with respect to r, right? Which is odd, right? But that's actually a fluke, right? Oddly enough, right? It's not all shapes do that. It's weird. It's just something that happens. But prove to me that the surface area of a sphere is 4 pi r squared, right? Or a squared in this case, right? Well, the way we do it is we need a suitable parameterization, right? A suitable one is spherical coordinates, isn't it? Right? The radius is fixed, so we've got a sphere of radius a, and my 2 angles u and v, or they're acting like theta and phi. I want the whole sphere, so you remember theta goes around the y axis anti-clockwise, so I need theta going from 0 to 2 pi, or u going from 0 to 2 pi. And the angle phi measures from the positive z axis down, I need phi or v going from 0 to pi. And once I've got all that, then I'm going to do a surface integral, which is not pleasant in this case, but it gets there, and eventually gets there. That's what we're going to do in the next lecture, right? So don't worry about looking at that one yet. Just go through the parametric representation of surfaces, right? And I say we're going to keep it easy. Brute force it, cylindrical coordinates or spherical coordinates. So it's not going to be like lines where we have to do certain other things. And I also will do a different example as well in the next lecture. But work through, not this one, work through example sets 1 and 2, right? And then in the next lecture we'll actually work out how we do these integrals to calculate surface areas. All right? But we'll leave it there for today. Okay? I don't want to get started on the next one without having more time. All right? All right, thank you everyone. I'll see you all tomorrow.